Hi, everyone. Welcome to tonight's Star Party. I'm going to do a little bit of an intro and some housekeeping before we introduce the speaker. So tonight's going to flow a little bit differently. For starters, people in the auditorium are seeing me on the screen, and that's a little bit different. At the end of Dr. Marshall's talk, we will have questions. There will be a microphone in the auditorium if people would like to ask questions that are here. And if you are on YouTube or on Zoom, you can put your question into the chat box and we will take them that way. So, and then for those on Zoom or on YouTube, after the talk and after the questions, we have a little bit more of a program. And for those of you on the Hill, then you can go for your dome tour after that. So I'm just going to introduce Lori, who's going to introduce our speaker.
Hello, everyone. Thank you very much for coming both in person here and also online. And we are happy to have Dr. Madeline Marshall back for us again. But I first of all wanted to give a land acknowledgement, because this is really important, that where we are here on what we do call Observatory Hill has actually been the land of the Wasanic people who's for centuries. And they call this hill Watixis. And we want to make sure that we are acknowledging that we work and we play here on this hill, and that we are very thankful to have both the land and the sea around us and the sky above us in order to be able to work here. So thank you to the Wasanic people for letting us be here on the Hill. So tonight we're really pleased to have Dr. Madeline Marshall back with us again. She was with us online in December, where I gave a presentation on what was going to be happening with the James Webb Space Telescope, and in fact, I think it was Madeline, you were on the 18th of December, and it went off on the 25th. So that was something. Madeline comes from Tasmania, and she works on black holes and other kinds of very mysterious things out in the universe. Now, Madeline, you might want to introduce yourself a little bit more, maybe give a little bit of some background to the people that are in the audience, if you'd like, before you start. But now that the JWST has put out some of these beautiful photographs lately, that's what she is going to now talk to us a little bit about, and then give us some information, so that when she starts her own programs fairly soon, I believe, is that right, Madeline? It's going to be quite soon, so that we're just going to have to completely book you for about another 4 or 5 months from now before you start off. So I'm going to turn it back over to you. Okay, thank you, Madeline.
Thanks a lot, Lori. Let me just share my screen before I get started. Okay. Put that there. Okay, so I'm assuming you can hear me and you can see my slides. And if you can't, please complain now. Cool. Okay, so I'm really excited to be back here. So as Lori said, Wes Fraser and I gave a presentation back in December about the launch of Webb and what our projects would be doing with Webb. And so it's been a very eventful 6 months between then and now. So I'm sure you're aware, Webb is in space now and actually taking observations. But before I start talking about these first images that were released this week, I did want to give you a brief overview of what Webb actually is, in case you didn't know. I'm sure most of you do, but just in case. So the James Webb Space Telescope, as I said, so it was launched on Christmas Day last year. And it's been in the making for decades now. And so it was a very anticipated launch. And so from French Guiana, it was launched in its rocket out to a location in space called L2. Now, L2 is 1.5 million kilometers away from us on Earth, and it's a bit more than 4 times further than the moon. And so Webb sits out there, and on its journey, you can see it on the top right here. On its journey, actually, this is a picture of it above the Earth on its way to do some really awesome science. So the exciting thing about Webb is that it's the most complex and exciting space telescope that we have ever launched to space. And it's really a successor to the Hubble Space Telescope. So it's not a replacement for Hubble. Hubble's still up and running and still finding out all sorts of great science, but it's a kind of a successor. It's doing something new and exciting. So Webb, one of the key exciting things about Webb is the sheer size of the telescope. So here's an image of what it actually looks like. So it's got this beautiful gold mirror in the hexagon shape made up of lots of little hexagons. And so the reason that it's this weird shape and made up of little mirrors is that this mirror, which is about 6.5 meters across, was too large to fit in the biggest rocket that we have on Earth. And so to launch it into space, it actually needed to fold up. And so these side panels actually folded in, and it was kind of like tucked away for launch so that it could actually fit in the rocket. Everything else that you can see here was also tucked away. So there is the secondary mirror and also this big sun shield. And so this shields the mirror from the Earth and the sun. And so this is the size of a tennis court, this sun shield. So it just gives you some idea of how big this telescope is that is now up in space. And so in astronomy, the bigger mirror you have, the better your images will be. And so Hubble, for reference, is 2.4 meters in diameter, and we're now at 6.5 with Webb. So this is a massive difference in terms of image quality and the kind of depths that we will be able to see into the universe. The other big difference with Webb and why it's kind of so exciting is that it's actually an infrared telescope. So if you think about the wavelengths of light that we can see from the purple and the blue all the way to the red. And so this is what we call visible or optical wavelengths. So if you go a little bit bluer than blue, we get UV, which burns us from the sun. And if we go a little bit redder than red, we get to the infrared. And so there's nothing extra special about the infrared or the optical. Our eyes are trained to see just the optical. But there are some animals that actually do see in the infrared, just like we see red, they see infrared. And so like mosquitoes and bats can actually see infrared light. So the key thing about Webb being an infrared telescope is it can actually see different things than Hubble could see. So Hubble was a UV, optical, and slightly near infrared telescope, but Webb covers basically the whole infrared. It's really opening up new wavelengths that we haven't been able to access before. And so these new wavelengths give us a key to see through dust and dusty regions and to see into the depths of the universe, to see the first objects that formed. So I'll talk a little bit about that as we go through the images. So I guess then the next thing to do would be to show you all of the beautiful images that were released this week. So these are the first images from Webb. And so these were done, it's called early release observations. And this was basically planned to come up with some beautiful images showcasing the capabilities of Webb. And so the science teams decided on these 5 specific targets to really highlight how fantastic Webb will be. And so of the 5, we've got a galaxy cluster, we've got a stellar death, interacting galaxies, stellar birth, and an exoplanet. And so I'm going to go through these one by one. So let's start with the stellar birth. which might be one of the prettiest ones. I'm probably going to say that for each of the 5, but I think this one might be the prettiest one. If you're an astronomer and you're keen on positions and facts, I've got the details here of the Carina Nebula, which is what this is. But let's face it, we all want to look at the image. And so that is what we see here. So this is Webb's view of the Carina Nebula. And so what we're actually looking at here is a stellar nursery. So this is a region in space in our galaxy where stars and planets form. And so what this brown area at the bottom is dense clouds of gas and dust. And so stars form from dense clouds of gas and dust. And so most of the stars that we see in this image are actually baby stars that have really only just formed. And so, as I said, the exciting thing about Webb is because of the infrared, we can actually start to peer through the dust and actually see these stars forming. But I'll talk a little bit about that in a moment. I wanted to zoom out first so you can actually see what part of the universe we're looking at here to give you a bit more of an idea of what's actually going on. So this I found on Twitter, where all good information can be found. This is the Karina Nebula, the whole thing. So this is a big region of star forming. It's a star forming region within our galaxy. And so if you zoom in on this little box right up in the top corner, we get this image here. And so you can see this, we've got this big, I guess, circle, a big sphere. And so what this is there is a star at the center of this sphere that has a very, very bright star, has switched on and effectively gotten rid of the gas around it. And so it's pushed that gas out. And so that's what we see. We see the edge here of the gaseous structure. So if we zoom in again on this box, we get this box down here. And then this box is the view that Webb has taken. And so we're seeing this brown wall, really, this wall of gas that is has been pushed out by the star, sorry. Okay. So the first image I showed you, so this is just with NearCam. So there are basically 2 purely imaging kind of instruments on Webb. So NearCam, the near infrared camera, and we've got MIRI, the mid infrared instrument. So this is the near infrared. And so if we go to MIRI, we're looking a bit more further into the infrared than before. And so the further into the infrared we go, the more we can kind of see through the dust. And so that's what we're seeing here is a combined NearCam and MIRI image. And so you can just see all of these stars just forming in our galaxy. And it's such a beautiful picture as well. I think it's one thing that you kind of have to remember as we go through these images of these are actual images of our universe taken by a telescope. Like some of these are so beautiful, you'd think an artist has made it for a museum, but these are actual pictures of where we live in the universe. So now we can compare to Hubble. So Hubble up the top and Webb at the bottom. And this, I think, really highlights what I was saying about being able to see through the dust. So Hubble, as I said, so it's optical, a little bit infrared, but James Webb's all in the infrared. And so you can actually see the depths that it can go to. So with Hubble, you hit the dust and it's kind of like a solid wall. You can't really see any structure. It's just a flat kind of blob of gray. Whereas with Webb, we can actually see through and actually see all of the kind of 3D structures within that star forming region. And so you can also see, these 3 red stars here are the same 3 stars here. We can obviously see those in Hubble, but there's a lot that we can't. So if we see these 3 stars up here, these 3 yellow ones, we can't actually see them in Hubble. And so these are actually stars that are in the gas cloud. And so with Hubble, because we can't see into that gas cloud, we haven't seen the stars. And so by going into the infrared, we can actually see these regions of star formation and regions where planets are forming to really understand how solar systems like our own formed. Okie dokie, let's go to the next one, which is the opposite end of a star's life. So they, the ones I showed were stars being born. And now this is a star at the end of its life. So this is the Southern Ring Nebula, or you might know it as the 8-burst nebula as well. So this is a planetary nebula. And so it's called a nebula like the first one, but it has absolutely nothing to do with the first one. It's just the name, unfortunate name choice. And so what we're seeing here is a star, or actually 2 stars at the center of this ring. And one of them has ended its life as a star. So it has run out of material for nuclear fusion. And so as it's run out of fuel, it has kind of puffed up and ejected layers of gas. And so what we're actually seeing here is these rings of material that were ejected from the star at the center. And so now that star, which is actually not the one we can see here, this other star is a white dwarf. And so this is just the dense, inert core of kind of what was left over from the star. And so, yeah, so you can see these multiple rings as the star has burst a few times. And so that was with NearCam. We can go again to MIRI and have a look as well. And what I find the big difference between the NearCam, which is the near infrared, and MIRI, the mid infrared, is the center here. So I said that there were 2 stars, and you can actually in this second image see that second star. So this white dwarf, you're actually seeing it here. And so this is the one that's died. This other star is its companion star. This is a binary system. And so just zooming in further, because it's such a beautiful image, you can just see how much structure we can see from this Webb image. So this reminds me of a sheep, or maybe like a brown poodle with all this beautiful kind of fluff. You can see these kind of rays, and what these are. So these, I guess they're lines pointing towards the center of the star and coming outwards, if you can't really see what I'm referring to here. These are little holes in that gas where the starlight has been able to come through. And so that's what we're seeing there. And these other things, this one here particularly is a side-on galaxy. Here's another galaxy, here's another galaxy. These are all galaxies in the background of this image. And so with Webb, it's so sensitive that we can start to see galaxies everywhere we look, even when we're really not wanting to find them in this case. Okay, so back to our friend Hubble. This is what Hubble saw when it looked at the Southern Ring Nebula, and this is what James Webb can see. So you can just see how much better this image quality is. It's really like 3-dimensional now with all of that structure. It looks very beautiful. Okay, on to the exoplanet. This one's the most scientifically complicated of all of them because it's not an image, it's a plot. But I'll try and explain that to you all. So this is an exoplanet, and what that means is it's a planet that orbits another star other than our sun. So this is the actual data from Webb. This is just a representation of what's going on. So we can discover in our galaxy planets because of their transit. So you may have seen transits of Mercury or Venus, and it's very similar, pretty much exactly the same phenomenon that we're looking at here, but of a different star. So what's happening is the planet orbits the star, so it's going around in a circle here. And if the alignment's just right, that planet will actually pass in front of the star. And so if we measure the starlight as a function of time, so we're measuring it, and then the planet comes in front of the star, what will happen is some of the light from the star will be blocked. And so the star will appear dimmer just for a little while. So that's what this is here. So Webb observed this star. It was going along, and then all of a sudden the star got dimmer. And then once the planet had passed in front, so it's come out the other side, and then the star is back to its normal brightness. And so using this method and a few other methods, we've actually discovered about 5,000 exoplanets, so planets orbiting stars that aren't in our solar system. So to give an idea about the kind of scale that we're talking about here, the difference between the starlight and the dimmed star is less than 1.5%. So this is a really tiny effect. So this image is not at all to scale. The planet is very, very small. So you have to have very, very precise measurements to be able to see that dip. In terms of the time scale that this actually happened, so this whole observation took 6.5 hours. So Webb observed the star for 2.5 hours beforehand. The transit itself took about 2.5 hours, and then there's another 1.5 hours afterwards. And so Webb took an observation of this star every 1.5 minutes. And so that's what we're seeing here. This isn't the cool part. This is just the background of what we've actually done. So instead of actually just taking an image, Webb took a spectrum of this star as the planet was undergoing this transit. And so what is a spectrum? So I'm sure you've seen rainbows before. And so when sunlight passes through some prism, its components actually get spread out into a rainbow. So the actual light contains all sorts of different wavelengths, but we just see it as one white light. And so that's true for all light. All light is made up of multiple different wavelengths. And so we've got wavelengths from the ultraviolet through to the visible of colors and then into the infrared. And so by splitting up the light that we see, so when we observe that star that has this exoplanet around it, we can split up that light and actually see what components is that light made of. So if we imagined that our Earth passed in front of our sun and someone else was to observe us through this same phenomenon, this is kind of the thing we'd see. So if you are at the top of this line, so these bits here and here, none of the starlight is being blocked at all. But what happens is if there are molecules in the atmosphere of that planet, those molecules will absorb certain wavelengths of light. So we know based on lab experiments that water will absorb certain wavelengths of light, methane, carbon dioxide, our ozone layer, and so on. And so each molecule will absorb a different wavelength of light. And so if we see that there's a certain wavelength missing, we know that that must be because there's that certain element in the atmosphere. And so this is how we can determine what is in the atmospheres of other planets. And so this is what Webb's done. So this is an artist's impression. This is the actual data. I'm sure it's not the prettiest data you've ever seen, but it's very exciting. So here we have the spectrum of this planet. And so instead of having dips down, like we saw before, we actually have dips up. And so what this means, because they're going up, it means that the planet is actually very, very hot. And in fact, based on this data, we have determined that the planet is 725 degrees Celsius. So maybe not the best place to live. But the other exciting thing, and the main exciting thing about this image, is these humps that you can see. These are at the wavelengths that water emits or absorbs. And so we know that there is water in the atmosphere of this planet. Now, that doesn't mean it's habitable. Obviously, it's 725 degrees, so it's a bit hot for me to go there. But also, it's a hot gas giant planet. So it's not a rocky planet like our Earth. It's basically like a Jupiter, but very hot. It orbits its star very rapidly every 3.5 days. So it's really close to its star. So that's why the planet's so hot. So this water is not in water form, it's in steam. And so there's a steamy atmosphere around this planet. So this isn't the first time that we've discovered water around other planets, but this is really just the beginning of what Webb can do, and it shows that it's capable of doing this. So it's able to see much more distant planets than we were capable of before, and also see wavelengths that we weren't capable of seeing before. So we can see elements like methane and oxygen in the atmospheres of these planets. And so that's a big key aim for Webb, is to try and find, maybe habitable planets in our galaxy. Okay, so then we've got a galaxy cluster. And so this was the first image that was released. It was released on Monday in a sneak preview by Joe Biden. And so this is our image here. And so pretty much every speck of light in this image, except these very spiky ones, is a galaxy, not just a star, but a whole nother galaxy. And so these are really, really helpful for studying the very early universe. And so at the time that this was made, this was the deepest, crispest view of the near-infrared universe that we've ever seen. But that record may not even currently have held up. This is a very shallow image compared to some of the amazing things that we're about to do with Webb. So at the moment, we'll call it the deepest, but it won't last for very long. So what are we actually seeing here? So this is a galaxy cluster. I'll go back here. So these white galaxies in the center are actually all in a group together. So spatially, they're interacting and orbiting one another. And so these have quite a lot of mass. And so they are bending the light from galaxies behind them. So from Einstein's theory of general relativity, objects that have mass actually warp space-time. And so what happens is there's a very massive object like a galaxy cluster. It will warp space-time so that instead of the light traveling directly from the galaxy to us, it will actually bend around the galaxy cluster. And so this bending of light actually distorts the images that we see. It also magnifies the galaxies, which means that we can actually see galaxies that would be too faint otherwise. And so that's why we like to observe galaxy clusters, is because they're like a cosmic, what are they called? My brain's had a blank, a magnifying glass. And so they make the things behind it look bigger, but they also make them look distorted. And so you see these arcs here. And so these are pretty regular, normal shaped galaxies, but they've just been stretched by that gravitational lensing effect. And so these are really helpful for studying the very early universe because they appear bigger than they otherwise would. So if we were to look at this galaxy normally, it'd be pretty small and probably pretty faint, and we wouldn't really be able to tell much about it. But because it's so magnified and really stretched, we can actually start to see lots of the different details within that galaxy. So that's what we're looking at here, a galaxy cluster. Some galaxies are being lensed, and then there's lots of just other background galaxies as well. So zooming in a little bit further, there is one galaxy in particular that I'd like to talk about. And it's this tiny red dot here. It doesn't look like much, but this galaxy is actually 13.1 billion years old, or 13.1 billion light years away. And so how do we know that? So as we talked about spectra already, the elements in a galaxy emit at certain wavelengths. And so galaxies have kind of a typical pattern of what they look like. And so what happens is the universe between us and the galaxy is expanding, and that actually redshifts the light. So if the light was originally blue, it will be red. If the light was red, it will be infrared. And so based on the patterns, we can see where these emission lines from those elements within the galaxy, so this certain pattern, so we've got a pattern here, as the galaxy gets further and further away, the pattern gets shifted further and further into the infrared. And so by determining how far this pattern is shifted, you can determine how far away that galaxy is. And so that's what was done with NearSpec, which is a spectrograph on Webb. so near infrared, NIR spec. And so this is the spectrum that we get from this specific galaxy. And so based specifically on the pattern, so this hydrogen and 2 oxygens next to each other, that's a very recognizable pattern. And so based on that, we know that the galaxy is at redshift 8.5 or 13.1 billion light years away or years old. And so from this spectrum, not only can we determine the distance to the galaxy, we can also determine what it's made of and what the conditions are in terms of the physical conditions. So we can see oxygen, hydrogen, and neon in this galaxy and try to understand, is it highly forming stars, or what's actually going on in this galaxy. And so this can tell us a lot about the physics. So here's a comparison from Hubble to Webb. And so this, I think, is a little bit of an unfair comparison because this isn't the best image that Hubble has ever taken, but you can really see how much of a difference Webb can make in terms of the detail as well as the depth, so into seeing so many more galaxies. But I think maybe a little bit more realistic comparison, Hubble was awesome. We don't want to forget how great Hubble was, and this is one of the best images that Hubble has taken of a galaxy cluster just like this. It's not the same cluster, but you can see it's capable of doing a really fantastic job at observing. But Webb will be better for observing the distant universe because going further into the infrared, we can see further back into the universe. Okay, so the last of the 5 is Stefans Quintet, which is a series of interacting galaxies. And so what we've got here, so we've got 4 galaxies, 1, 2, 3, 4, that are interacting with each other. And then this 5th one on the left, which isn't actually anywhere near these other 2. It's actually much, much closer. I think it's 7 times closer to us. It just happens to line up on the sky. And so this system is really interesting because these galaxies are interacting and merging with each other. And so this is really helpful for understanding galaxy formation and evolution because mergers are a very, hectic but important part of a galaxy's life. And so with Webb, we can actually really see this dust flame, which is caused by these two sets of galaxies, these 2 and this one, actually merging together. And you can see it's really heated up that gas, and we're now seeing that feature. So that is both NIRCam and MIRI. This is just NIRCam. And so you can see it's more looking at just the stars. And it's MIRI here, this is just MIRI, that sees all the gas in the galaxies. So if you look here, so we're looking at the stars, you can see actually like lots of little points of light here. But here we're looking at the dust lanes that are forming these galaxies. And you can see that dust between the merging galaxies. Also, there is here what I study, which are supermassive black holes. This galaxy at the top has this shining supermassive black hole. This like 6-pointed spike here is a shining supermassive black hole. This weighs 24 million times the mass of our sun, and it is so bright that it is 40 billion times brighter than our sun. And so this is really cool to be actually able to see that Webb can observe these systems because my research is trying to use Webb to observe supermassive black holes. So this kind of excited me the most. And so here's a comparison between Hubble and Webb. So again, Hubble isn't shabby at all. It's a really beautiful image. But now with Webb, we're seeing much more of the dust in the galaxy. So the dust lanes that are actually forming the stars. Okay, I did want to just briefly mention that with this supermassive black hole, this also showcased another kind of spectra that can be taken with Webb, which is integral field spectroscopy. And so what that means, instead of having a single spectrum of the galaxy, we can have a 2-dimensional spectrum. So at each point of light, we get a spectrum. And so here we can see, so this is the center of the supermassive black hole at the center, and this is a little bit away from it. We can actually just using the one observation, get a spectra of both regions and determine all sorts of different kinds of physics. And so by being able to do this two-dimensional spectroscopy, you can actually get like an actual three-dimensional view of what's going on and really detailed physics about all sorts of things in our universe. Okay, so they were the 5 images that have been officially and beautifully released so far. But I did want to really mention that that was just the start of Webb, and lots of science observations have already been taken. And so scientists got access to our first data on Thursday. There's a lot of publicly available data sets that all scientists around the world are trying to use to find some cool things. And so I just wanted to briefly mention and show a few of those. They're all unpublished and unpeer reviewed, and I found them all on Twitter, but they're still really exciting. And I just wanted to show you that we're actually using Webb now for science. So here we've got to spot the difference. And there are a few differences, but there's one key difference. And you might have been looking at this enough now to notice what it is. And so I'll point it out to you. The key difference is this single point here. And so this was a Hubble image taken back in 2011. And this is now 2022 with James Webb. And there is a single point of light here that was not there when it was observed 11 years ago. And so this maybe, don't want to confirm anything, could be a supernova that's gone off in this galaxy that Webb's actually caught, which is pretty cool. Here is an absolutely beautiful image of a nearby galaxy by the FANGS team. And so this on the left is the Hubble image. And they've got this image on the right with Webb with all of those dust lanes, as we've been seeing with the other galaxies before. So that's just a beautiful one. And then finally, not so pretty, but some people are very excited about this, is, I'm hoping you all know what this is. This is Jupiter. This is not a nice science image. This was not intended to be beautiful. What this was part of the commissioning of Webb. It was to check that Webb could actually track something that moved on the sky. And so NASA released it because it was kind of cool and people liked Jupiter. And so you can actually see one of the moons of Jupiter as well in this image. Okay, so I think that's it. Yep, that's all of our 5 fantastic images that we've seen with Webb and a few new sneak peeks at some other things. So as science progresses, there will be all sorts of exciting press releases and science results and beautiful images coming out as astronomers do our first science with Webb. This is just a very quick preview, the first 100 hours of observations, but the real science is really about to kick off. And yeah, it's a very, very exciting time to be doing astronomy and watching astronomy from the news. So yeah, thanks a lot.
Thank you so much. That was amazing. These images are just still so stunning every time I see them. So we'll take some questions. So if you are online on YouTube or on Zoom, you can type your question into the chat box. But if you were in the auditorium, Calvin has a microphone.
Yes,
and
I'm right here. Can you hear me?
Yeah, we can hear you.
Beautiful. Okay, yeah. So if anyone in the audience here has a question, you can raise your hand and I'll point the microphone at you and you can speak clearly and ask your question. All right, I'll start with you here.
You know what neutron stars are made out of?
Yeah, so neutron stars are actually made out of the exact same material that the white dwarf at the center of this nebula is made out of. So what a neutron star is, well, I guess maybe I should start with a white dwarf first. So what happens as a star evolves is that the core of the star undergoes nuclear fusion. And so it produces heavier and heavier and heavier elements until it gets to iron, if I remember my chemistry correctly, and then it stops. There is no benefit of going any further than iron due to physics. And so then the star will run out of gas And the core will just be left up of all of those materials that the fusion produced. So elements ranging from, you're really testing my chemistry knowledge here, everything from hydrogen all the way down to iron. And that's in just this kind of big core at the center of the galaxy. That's the center of the star. Sorry, I'm a galaxy person. I've got galaxies on the brain. So this is at the center of the star. And so what happens when the star, if it's just in this case, the outer layer puffs up, you're left with a white dwarf. So it's just the core, nothing exciting has really happened with it. If the star is big enough, instead of puffing up like this, the star will actually explode in a supernova explosion. And so that material, that just the core of the leftover materials in the center of the star, because of the explosion, there'll be a lot of pressure and that will all collapse in on itself. And so there is so much pressure that the elements in the material are pushed together so closely that their neutrons touch. So usually you have a neutron or an electron orbiting a neutron. And so that's kind of the density of a white dwarf. You have kind of your electrons almost touching each other. But this is so compressed that all of the neutrons touch each other. But it's still actually made of the same kind of, it's still just the leftover core of the star, if that makes sense. And so if you go further, if you have a more intense explosion, because your star is even bigger than what we'll call a neutron star, you actually get a black hole, which again is the same matter, but it's compressed to the point where it's so dense that basically it becomes so dense that gravity kind of breaks down in a little bit of a sense and that light can't escape. And so yeah, the core is always kind of just what was left over from the star's life. It's a long way of answering that question.
Can I ask one of the online questions, Calvin, and then we'll go back to the auditorium?
For sure.
So there's a question which starts with, sorry if you mentioned it, but how wide is the Karina Nebula? The galaxies in comparison look so minuscule.
So let's have a look. I wrote the information down because I can't retain that in my brain. So Karina Nebula, it's the first one. So here we are. So the actual image is 16 light years across, or 7.3 arc minutes, if that's your style. But in terms of the whole structure, so the whole thing was 460 light years, but then we're zooming in really only on the 16 at the center. But so these are big structures on our sky. The galaxies are much, much bigger, but they're much further away. And so we see them to be obviously much smaller.
Thank you. Calvin, do you have another question?
You've got another question right here.
Can the James Webb Telescope see the blue monster stars, which were apparently the first stars?
I don't know. Oh, so the first stars in the universe, do you mean?
Yeah.
Yeah. So that's the hope. We really, really hope that it can. So in the beginning of the universe, there was really nothing. It was just hydrogen and helium. And at some point, the first stars and the first galaxies formed. And so because the light from those very, very distant objects is very redshifted, all of that light is in the infrared. And so we haven't had the capabilities to actually search for them yet. Now we have Webb, we have the capabilities to see things that are infrared. And so if these things are bright enough, we should be able to see them. And so there are a lot of theories. Some people say we'll be able to see them, and some think that they'll just be too faint and we won't. But this will definitely be the best instrument for doing it. So yeah, that's a really good question.
Okay, I'm going to ask you another one of the online questions. Is there a similar density of galaxies regardless of their direction, regardless of the direction the JWST is pointed?
Yes. As a whole, the universe is very uniform. And so generally speaking, wherever we look is kind of the same. That said, locally, and particularly on the scale of our Webb camera, which is pretty small, there are regions that are more dense than others and less dense than others. And so from experiments with previous telescopes, we know some regions that are quite dense. And so they're really good targets for Webb, because we know that with one pointing, we're going to get more galaxies than usual. Because we'd be ashamed to point somewhere that had less galaxies than usual. Though that said, there's galaxies absolutely everywhere, and there's so many of them. So on a small level, yes, it actually does vary, but on the the universe scale, it's very uniform.
There's a question here in the audience.
This might not be related to the James Webb Telescope, but how big is the biggest black holes in event horizon?
So the most massive black hole, I always forget this, I think it's 100 billion times the mass of our sun, which is very, very massive. I'm not sure how large it is in terms of its physical size and its event horizon, but they're very small given how massive they are. So the Event Horizon Telescope, that's the one that's been observing supermassive black holes, and so we've seen 2 of those. Of those 2 that we've seen, those supermassive black holes that weigh about 1 billion times the mass of our sun, their shadow, the black hole shadow that you see in those images, is about the size of our solar system, so out to Pluto. So there's 1 billion times the mass of our sun in just our solar system of space. So they're very, very massive.
Somewhat related, I have an online question about how does the supermassive black hole shine if we can't see them? What is it that we are seeing?
Yeah, that's a great question. So this is my research. So the black hole, obviously it's a black hole. Nothing can escape the black hole, even light. But it is gravitationally affects things around it. So at the centers of galaxies, if there's any gas or dust or even nearby stars, they will be gravitationally attracted to that black hole. The way that gravity works is that that material will form a disk. And for that disk to be stable gravitationally, the disk has to rotate extremely rapidly. And so that disk, anything that rotates is fast gets hot, and anything that is hot radiates energy or light. And so these accretion disks are actually the brightest objects in the universe. And so we call these quasars, these accreting supermassive black holes. And so we're not actually seeing the black hole itself, but that accretion disk, that super bright accretion disk of matter spiraling around that black hole.
Okay, we have another question here.
How do black holes keep the memory of what they've absorbed in them enough? Don't they self-destruct, basically, like over a lot of time?
Yeah.
How does that work?
Yeah, over trillions of years, they will decay. And so there's a very complicated phenomenon that I don't really understand much, which is called Hawking radiation, after Stephen Hawking. And so the idea is that the matter can split into 2 photons, and one will face inwards and one will face outwards, like if this is on the event horizon. And so this is extremely rare, but eventually that can happen, and then you'll get a photon escaping from that black hole. And if that happens enough over trillions of years, your black hole will evaporate and nothing will be left, because this process is extremely unlikely, and it only happens like 1 atom at a time. But over trillions of years, anything very unlikely can happen. But yeah, it's very bizarre, abstract concept, because really everything else in the universe will not really exist by then. Like all of the galaxies will have died and be very boring. So, the black holes will be the last thing that's kind of left.
Calvin, is there another question in the
Yes.
auditorium?
We've got another question here.
Lots of questions today.
Yeah, hi there. Is Webb capable of seeing exoplanets, so planets outside the solar system directly?
Yes. So I showed you the spectrum of a exoplanet that Webb can measure. But yes, it can actually observe exoplanets on the sky as like an actual image. I came across this by accident yesterday because I was looking through the archive. I was looking for an image of a star that Webb had taken. And I clicked on one and I thought that this was a star, and it turned out it was actually an exoplanet that had been observed. So I have seen one with my own eyes. You can actually see them in terms of a physical picture, not just the spectrum.
Calvin, do you have any?
Yeah, a follow-up.
Okay.
What's the Canadian contribution to the Webb telescope?
Yeah, so Canada contributed two very important parts of the telescope. One, I might say, is the most important part of the telescope, is the fine guidance sensor. And so what that does, it's not actually a science instrument itself, but it points at the sky and determines where Webb is pointing and where it needs to point, and keeps the instrument stable. So it will find what's called guide stars on the sky and work out where it is and then hold it there. So without the fine guidance sensor, you wouldn't get any of these observations that we've seen. The other instrument, which is actually a science instrument, is called NIRISS. So the near infrared, I had a blank, imager and slitless spectrometer, but I feel like the R's in the wrong spot. Anyway, it does imaging and slit spectrometry. And so that's actually the instrument that took this spectrum. And so that can take both images and spectra of galaxies and planets and all sorts of things. And so that does all sorts of cool science. So we've got a very important role in keeping the telescope pointed, but also actually doing some real cool science like this.
Okay, we have another question here.
So you mentioned dust a few times, and in the photograph of the birth of the stars, there's dust. Where does that dust come from and what's it made of?
So it's made up of all sorts of material from the leftover stars. So in the very early universe, the galaxies were just made of hydrogen and helium, because that's what was produced by the Big Bang. And then as the first stars formed, those stars formed different elements. And then as those stars exploded and went supernova, they distributed those elements across their galaxies. And so over generations and generations of star formation, they would distribute all of these materials amongst the galaxy. And so those will eventually clump together and potentially heat up, and all sorts of different physical processes which end up forming that dust. So in the very early universe, there was no dust, and it slowly built up over time.
I've got a question here, which is, how often does James Webb change its direction of observation?
Yeah, that's a good question. I don't know the exact answer. They plan the observations pretty carefully to minimize that, from what I understand. So lots of people want to observe in lots of different parts of the sky. And so I think they do it. So once one certain observation's been taken, they pick one that's not very far away on the sky, because you wouldn't want to have to look here and then do a full 180 and look at the other side. So the observation planning is very difficult to try and work out what to schedule when. But generally, once the observation's taken, maybe that will take 2 hours or 16 hours or 40 hours, depending on what you're observing. Once that's done, then it will point to the next thing, which hopefully is nearby.
Okay, we have one other question here.
Hello there. I was wondering if the Webb would allow us to do any more spectroscopy of objects in the solar system beyond what is possible right now.
Yeah, so the only things that Webb cannot observe in our solar system is the sun, Mercury, Venus, and Earth, because the way the sun shield is, it always has to point away from the sun, and so it can never see those planets. But it will do all sorts of cool science with our planets and the moons around the planets. So like the moons of Jupiter and Saturn are really interesting targets for searching for life, because they have potentially they're icy planets. So yeah, we can do lots and lots of stuff with our solar system with Webb, except for the inner solar system, because we literally can't turn the telescope around to look in that direction.
Okay, and then I'm going to ask you one last question from online, and then we will let you breathe for a second.
Do it all again.
So the images shown thus far involved relatively short exposure times. Are longer exposures planned, for example, of Stefans Quintet, and will these reveal more structures with the longer exposures?
I don't know specifically if Stefans Quintet will be observed again. Generally, observing longer gets you fainter things. So whether that be fainter parts of the spiral arms, but particularly it's really relevant for looking for the first objects in the universe, because they're so faint, you need to look for a long, long, long time. And so that cluster, not that specific cluster, but clusters generally will be observed for lots longer than the one that was. When you're looking at things close by like Stefans Quintet, it's not necessarily advantageous to just keep looking. At some point, you've kind of got enough information, and maybe you'd go to getting some spectra, which would give you some different information as opposed to just deeper information.
We will let you breathe, but I'm going to ask one more question, because I've heard a lot of young voices asking questions. So Madeline, how did you decide to study black holes? When did the spark kind of come for you?
Yeah. So I went to university. I was really interested in science and maths, but I didn't know what I wanted to do with that. I didn't know what my career would be. Honestly, I had never heard of astronomers. I didn't know that was a thing that you could actually do with your life. And so I took astronomy courses at university and thought it was really cool. And I kept going and I kept taking more astronomy courses. And then I started doing astronomy research courses and then astronomy research degrees. And now I'm here. So yeah, I had not had a lifelong passion. Like, I'm really excited that there are kids in the audience that are already keen. You're way ahead of where I was. So I'm very excited for your futures. But yeah, it wasn't something that I'd always planned or always, I never knew I could do it. So I'm really excited that this is where I am now. So yeah.
Thank you. And thank you so much for speaking to us today. So for the people who are online, hang on, we've got more for you. And for the people who are on the hill, there's a dome tour starting in a minute. So,
all right, thanks everybody.
Okay, so, and Madeline, you have your next set of, okay.
I kept it short, so I hoped that I would have quite a break between the two talks, but I had too many questions. A good amount of questions on it.
Good. Well, yeah. Thank you. And I'm going to keep rolling. So, yeah. I'm going to introduce Ruhi, and Ruhi is going to tell us a little bit about what's happening up in the sky right now.
Okay. Yeah. Roughly how long will that take? You're just wondering how long I have to.
No, so you have another link to join for the next one.
Yeah. Oh, yeah. I see.
Yeah, so then you can drop off and join, but I'd say give yourself 5-10 minutes and I'll tell them in the auditorium.
Cool.
Okay. All right. All right. Okay, and here is Ruby.
Hello guys.
Oh dear. Okay, perfect.
I'm not as tall as you, so I have to bring this down. Okay, guys. Hello, my name is Ruhi. I'm here to tell you what is up in the sky right now. And for all of you astronomy nerds out there who really like planets, but also really like your sleep, it's starting to become the season for planet watching. So right now we have Jupiter in the sky. It rises at around 11:53. And we can track Jupiter because it's a really bright star next to our moon, which is at a waning gibbous right now. Next to Jupiter, which does also set at 12:21 p.m. So if you are up from midnight onwards, you will see Jupiter rise from the horizon and up. We also have Saturn that rises up in an hour, actually. It rises at 10:25 p.m. And sets at 8:17 a.m. So you can actually get some shut-eye tonight, thank goodness, if you're going to do some planet watching. We also have Venus, which is now our morning star for the summer. So it'll be rising at 3:31 a.m. and setting at 7:26 p.m. So if you have to wake up really early for work this morning, you will be able to catch Venus, Saturn, and Uranus and Jupiter all at once as well. We also have the moon. Let's see, when is the moon rising? 11:30 p.m. and it will be setting at 9 a.m. tomorrow morning. So there are a lot of planets in the sky right now for you to keep an eye on. Remember, all you got to do is really just look for the moon. The planets will be in the general area of the moon. If you have a sky tracking app, the one I use is Sky Safari, really great. Just point it up at the sky and it'll tell you exactly where everything is and where to look and where to even point your own telescopes if you have one.
All right, perfect. So now if anyone has any questions for Ruhi, I don't know if you said, but Ruhi studies stars, the birth of stars, essentially, but also knows a lot.
A little.
So if you have any questions, you can just type them into the chat boxes. But I'm going to start you off with a question about redshifting.
Mm-hmm.
So Dr. Marshall had mentioned kind of how dating things, but how do we date things using redshifting? So do certain elements emit more when they are younger or older? Is that kind of how that works? Or
Okay, so when we're looking to measure things like redshift, we actually use a formula called Hubble's law. So the whole premise of being able to use this formula is we measure distance as we measure age, right? So if something is 100 light years away, that light is 100 light years old kind of thing. And so the further something is, we can measure its radial velocity, so how fast it's going. If it is going faster, because we know our universe is expanding, the faster something is going, the further it is from us. And so we are able to measure the distance using its velocity. We plug that into Hubble's law, and then that actually gives us our redshift. We can also measure it from spectroscopy, which is also tied in with Hubble's law. So we have things that we know the signature of, like how our speaker was talking about, of like oxygen and hydrogen. We know where they sit on a regular spectra, and then how far red shifted or blue shifted something is, we can tell what its proper redshift is and see how far it is as well.
Okay, thank you. So it's great to see the first images of JWST, but are they already starting to work on or imagine what the next telescope is going to be that's going to take the place of this one?
Of course, always. I feel like telescope engineers never really get a break. They're always trying to make the biggest and newest telescope as well. I'm not really sure what the main idea is past James Webb. Of course, this is really exciting, but we're trying to be able to send telescopes even further than the Lagrange point past the moon. Apart from even telescopes on Earth, like we're trying to build the 30-meter telescope as well. So there are always bigger telescopes to be built in the future, always.
What is the mix, let's say, of gases that's required to produce a new star? Is there a certain kind of recipe for a new star to come together?
So stars are primarily just made of helium. Hydrogen. Hydrogen is the main one. We make helium afterwards. So about 90 99% like hydrogen was the first element to ever be created after the Big Bang. It is the most simple element. It is the one that is the most abundant in our universe. So it is the thing that makes up most of our stars. And then after all of these gases kind of, they come in on each other and they start forming these stars, which is a little bit of helium, like a tiny little fraction of it, maybe like 2%. Most of it's actually hydrogen. And then after fusion starts, that's when we get everything else. But it always starts with hydrogen. That is our main key thing.
Okay. So there was a couple images there that we saw from JWST that kind of had the clouds, right? Which would likely be those gases coming together, that hydrogen. What is the kind of temperature that needs to, is there a temperature, I guess, that those need to reach in order to birth a star? Or is it like?
Yes, and a little bit. Okay, so when all of this gas is just on its own, is about like the temperature of space is about 2.7 Kelvin, which is incredibly cold. 0 Kelvin means there's absolutely no movement of molecules. So it's incredibly cold. But as you get all this gas kind of swirling in on each other, you can reach cosmic temperatures trying to create these stars. But because these stars are so deeply embedded in this gas, you can't actually see it with optical. And you just see kind of like, because as the light leaves these huge gas clouds, it gets slowed down because of all of this gas it's hitting. And so you can only see them through like infrared or, yeah.
Okay. So a galaxy, I think, has like different parts of a galaxy.
Yeah.
Is there like, I don't know, like the maternity ward of a galaxy? where in a galaxy do
these are great questions. Okay, so let's take our galaxy for example. So the Milky Way has a lot of spiral arms, and you will find the more turbulent an area is in a galaxy, the more star formation you're going to have, because you're going to have way more collision, things interacting with each other, things falling in on each other. You usually find this in spiral arms of like the actual galaxies. Elliptical galaxies are a little different because they're considered dead galaxies. There's not a whole lot of star formation going on in them. And that's why there's no arms, they're just round little bulges. Unfortunately, they usually happen when galaxies like collide and a lot of this gas is expelled outwards. And so that's why when you have like spiral galaxies and you take an infrared image of them, you can see how much heat is in the arms of them. And that's where you know a lot of the star formation is happening.
So there was a question earlier about regardless to which way JWST is pointing, will it kind of always be getting the same number of galaxies? But I think within a galaxy, like if you were looking closely at the actual galaxy, there are places where we get more stars and less stars.
Yes.
Is that okay?
Exactly.
Yeah. Okay.
It's just knowing where to look, which is also the hardest part.
Okay, so my last question, I think, is okay, so we see the clouds in the images as they, from the telescope.
Yeah.
But how, I guess, in these images from JWST, where are they in the life cycle of the star forming? And how long does it take from that? Okay, now here's a bit of hydrogen to, oh, look, we have a star.
Millions of years.
Okay.
Oh. Stars are a whole long process. From when the gaseous cloud starts collapsing onto each other, it is millions of years before that star even fuses hydrogen in its core. So it's a long way.
Okay.
JWST, I'm sure, will be also looking at different stages of star formation as well. We'll be able to look at things at like the initial stage of gas forming these small little clumps, which are large nurseries of star formation, to protostars, which is what I study, or like protostars with outflows, to just initial fusing of hydrogen, to like main sequence, dead stars, so on and so forth. Yeah.
Awesome. Okay. Well, thank you. I'll come and
Sneak away.
Thank you. All right. Well, thank you all for joining us this evening. If you are joining us from Victoria, Of course, we are open again during the day, during the week, if you're interested in coming up to the center from Tuesday to Friday, 10 to 2. If you are not in Victoria, you can always join. If you subscribe to our YouTube channel, you'll see every week when we have a star party. You'll be notified when that star party starts. You can also go to our website, become a member, and of course, follow us on social media. We're at Friends DAO on Instagram, Twitter, and Facebook. Thank you so much for joining us, and we will see you next week.